I'm a software engineer at a company called SitePen, predominantly working on enterprise web applications. I'm also a Google developer expert for web technologies, and you can find me tweeting at my handle, which is James L. Milner. So if you want to follow me or ask me any questions, that's probably the best way to kind of get hold of me. So yeah, I hope that this goes smoothly and that you learn something new. So before we dive too much into WebAssembly, I want to give a bit of an understanding about why WebAssembly kind of came about and why it came to exist. And one of the core reasons for its existence is that people have been trying to write native code in the browser for a very long time. And they've mostly been trying to do this through that avenue of plugins. So historically, you might have heard of things like ActiveX, which was kind of a Microsoft thing, and the Netscape plugin API, which kind of housed a bunch of other kind of platforms such as Flash, Java applets, and later on kind of Microsoft Silverlight. So then after about 2013, these things started to kind of die off. So Steve Jobs kind of killed off Flash with his announcement with the iPhone. And ActiveX kind of lost some of its momentum because of the advances in the web platform. So new things kind of started to take their place, though. So we saw the Google native client and associated APIs that came from Google, and that was an attempt to allow people to write sandboxed C and C++ code and run it in the browser. And Mozilla kind of had a different take on it. They created this thing called, they came up with this concept of ASM.js. And ASM.js is like a super strict subset of JavaScript, which compiles from C and C++. But because it is such a strict subset, it can do specific optimizations to make sure that the compiler can produce more performant code than just regular JavaScript. And so yeah, there's this like strong desire to write things that weren't JavaScript in the browser, which I love JavaScript, but I can understand why people would want to do that. And this is kind of where WebAssembly kind of comes into it, because WebAssembly is kind of inspired by some of these attempts. So some of you might have heard of WebAssembly in passing. Maybe some of you even looked into it. Maybe some of you even used it. But here's like a little refresher for everybody. So yeah, as I was saying, WebAssembly was inspired by those attempts. In particular, it's inspired by ASM.js. And the idea was that if we could compile from like C and C++ and a bunch of other languages to some very low-level language, then we could use that in this kind of sandboxed environment in the browser. So WebAssembly is this binary instruction format for a stacked-based virtual machine. And that sounds a little bit dry, but what that really allows us to do in the web is that it allows us to compile that C and C++ code into this kind of sandbox environment, somewhere where we could traditionally only ever write JavaScript like natively in the browser. And the cool thing about WebAssembly is it's kind of in keeping with a lot of the ethos of the web, and it's kind of trying to move away from this kind of plugin-based attempt to do things. And if you I think some of the interesting things about it are some of the design goals that go into it. And so the first of which is that it's going to be fast. So the aim is to have near-native performance. It should, and also not only near-native performance, but also consistent performance. So one of the problems with JavaScript is that sometimes the performance characteristics are like maybe unpredictable depending on which engine it's running on, or depending if it's like a hot path or a cold path. And so WebAssembly aims to always be predictably fast. It also has this like compact binary format. So because it's a binary format, it's like very well compressed, which means that it's smaller over the wire than maybe say something like JavaScript. It's also efficient to compile because it can be compiled like streaming compilation, and it can also be parallelized in its compilation as well. So it has like some really decent performance characteristics that kind of make it quick. The next thing is it should be safe. So the code is validated and it executes in a memory-safe sandbox environment. So this aims to prevent data corruption and security breaches, which are obviously quite important in the web because we've been spent so long trying to keep everything enclosed and to stop web apps from wrecking your computer. And the last thing is that it should be portable. So it shouldn't make any kind of architectural assumptions about the hardware that it's running on. It should support all modern hardware. It should interoperate with the environment and be able to interoperate with other WASM programs or other languages for that matter. So it should kind of be this universal thing that can ideally talk to kind of any environment or any other language. So yeah, those are the three things. It's going to be fast, safe, and portable, which on paper sounds pretty cool. But one of the problems with kind of a binary format is that it's quite hard to maybe understand what's actually happening. So alongside the binary format, we also have what's called the WebAssembly text format, which looks a little something like this. You don't need to worry too much about what this program is doing. It's just to kind of give you a feel for what the kind of text syntax looks like. So it's kind of this Lisp-like kind of representation. And the aim here is to try and make it easier to be able to debug your compiled WASM programs. So yeah, it's got this text format, which is really helpful. And as I was saying, its aim is that it can be compiled from a bunch of host languages. So you could take a program that's written in one language and then be able to compile that down to WebAssembly. So some example languages that currently have support for WebAssembly include Rust, C, and C++. Those are probably two of the most common languages for working with WebAssembly. There's also Kotlin. There's also a Haskell compiler. There's something called assembly script. So if any of you have ever used TypeScript, assembly script is essentially kind of a subset of TypeScript, which is quite a lot to wrap your head around because TypeScript is a superset of JavaScript. But anyway, long story short, it's a way of writing TypeScript and compiling it to WebAssembly. And lastly, Go. Go has a native compilation to WebAssembly. So yeah, we've got this kind of whole host of languages, and I think this will kind of only increase over time, and their support will only increase over time as well. So, number one question always get asked is, will it replace JavaScript? And the simple answer to that question is no. It's because WebAssembly's initial goal is not to replace JavaScript, because WebAssembly is very good at a specific set of tasks. It's very good at, for example, kind of numeric operations dealing with large sets of data very quickly. So you can replace hot paths in your JavaScript code or certain algorithms with WebAssembly programs to speed up bottlenecks in your programs. And you can also use it to open up a host of different applications that might not necessarily have been possible before because of things like performance limitations. So some examples of things like that are games is a great example, 3D mapping, or even 2D mapping because it's a lot of data-intensive work. Things like image manipulation or video processing or audio software. So these are just some of the examples of where WebAssembly might be a really great use case if you're interested in using it. So how do we use it? So I'm just going to show you a little code snippet of using WebAssembly from JavaScript in the browser. So it's trying to keep it as simple and sweet as possible. So what we've got here, if you skip the initial declaration and just look at where we go to webassembly.compile streaming. So we're using the WebAssembly JavaScript API, which is baked into the browser and also baked into Node. And we can do webassembly.compile streaming, and then we pass it the fetch, the response from our fetching the WebAssembly program. What that's going to do is it's going to compile the program, and then we're going to get the module, and then we're going to instantiate the module. And WebAssembly allows you to import things into it. So you can call JavaScript functions from a WebAssembly program. So in this case, we're just going to pass in a function called imported func, and it's just going to log out any argument that it receives. So that's the second line there, WebAssembly.instantiate with the imported object. And then next we're going to use the instance of the module to call one of our exported functions from our WebAssembly program. What that exported function actually does, what simple WASM has, is it's just a declaration of the number 42, and it just console logs out the number 42. It's probably like one of the most simple programs, and that's why it's called simple.wasm. So that's how you use. That's how you would use WebAssembly in the browser, or also in Node. So it's quite easy to get started if you're using JavaScript as your kind of host language for running WebAssembly program. So another response that sometimes you'll hear people say is that, well, that's all great, but we need to support a whole bunch of different browsers. And what's really cool is that WebAssembly support is actually really strong across all the modern browsers. So realistically, unless you need to support Internet Explorer 11 or Opera Mini, then you should be good to go. So 86% of the global market share can use WebAssembly. And if you desperately need to support IE11, most of the compilation tools, well, not most of them, but some of the compilation tools will allow you to compile your program not only to WebAssembly, but also down to JavaScript. So it can compile to, like mscript, and can compile down to ASM.js, which is what I was mentioning at the beginning, this like strict subset of JavaScript, and also WebAssembly. So it's not the end of the world if you have to support IE11, because you can just have a fallback down to JavaScript. And people who can support WASM will get the WASM file, and the people who can't get who don't support WebAssembly will just get the JavaScript file. And the other thing that I hear a lot is that, like, are people actually using it? So what I've done is I compiled 5 examples of companies who are actually using WebAssembly in production today. So the first of which is Figma. So some of you might have heard of Figma. It's kind of like a collaborative interface design tool. So you can create, if you're a designer, you can create mockups and share them with the rest of your team, share them with developers or whoever it might be. And they've leveraged WebAssembly to improve the loading times of the documents in their web platform. And what they found was that when they switched to using WebAssembly, the loading times for the documents, the designs, was sped up by a factor of 3, regardless of the size of the document, which is really cool. It's just this like linear improvement across the whole application. The next example I've got is Unity. So Unity is a games engine which has the possibility to compile your game to a WebGL target, so for running predominantly like in the browser. And they switched from using ASM.js to using WebAssembly, and what they found was that reduced the code size, the actual amount of bytes and the amount of code that's actually shipped to the end user. They found that it improved the performance, and it allowed them to grow the memory usage at runtime. So it had a whole host of benefits from switching. The next thing I want to mention is AutoCAD. So it's like one of the biggest CAD tools globally. And they had a 35-year-old code base, and they converted that to WebAssembly. So they were able to take this like hardcore desktop application and compile it to the web using WebAssembly, which is super cool. Like taking this 35-year-old code base and then just like putting it on the web. I think that's awesome. The next thing I want to give a shout out to is Squoosh.app, which is made by the Chrome Labs team. And this is basically an example of how to create a really performant web application. And it uses WebAssembly to do the image compression. So it's an image compression app, basically. Like you can upload an image and it will compress it. And the algorithms that they use are all the libraries that they use are all compiled to WebAssembly. And the last one I've got for you is eBay. So eBay use WebAssembly to they have a barcode scanner which was written in JavaScript, and they found that it wasn't detecting all of the barcodes that they wanted to detect. So what they did was they compiled a library from C down into WebAssembly, and what they found is that they could get 100% success rate by combining their JavaScript implementation of the barcode reader and the WebAssembly implementation. So that's 5 examples of people actually using WebAssembly today. So the next thing is, what about kind of like frameworks? Everyone wants to know if like you can use it with like Angular or React, or even like, can I just update the page using WebAssembly? And unfortunately, the answer is not yet, but it's getting there. So one of the limitations of WebAssembly currently is that it only really understands numbers. It doesn't have a concept of more complex types like strings or structs or arrays or objects. And this makes dealing with like complex types quite difficult. So for example, a DOM node is like a complex type. So there's a few things that need to happen before we can get to doing DOM manipulation in the browser or integrating with frameworks. So the first thing is, well, the first kind of step is that we need to, like, WebAssembly needs to be able to take a DOM node, and even if it can't understand what it does, it needs to be able to do something with it or accept that it kind of exists, right? So for example, you could take a DOM node, pass it to WebAssembly, and then do something with it with a JavaScript function that you passed in. And to do this, there's a specification called the reference types proposal. And the reference types proposal essentially allows you to do that. It allows you to take an object that exists on the JavaScript heap and then pass it through and then call it again on the JavaScript side. And essentially what this does is it allows you to avoid all this like glue code and passing, like serializing something in JavaScript, deserializing it in WebAssembly, and then serializing it again back to JavaScript. So kind of skips out these steps. And this proposal is, because it allows you to get hold of objects that are on the JavaScript heap, it's the first step towards garbage collection. And we need garbage collection because the WebAssembly needs to know if a DOM node has been garbage collected, because if you're trying to operate on something that has been garbage collected, you're going to have a bad time. So yeah, the next step is this kind of garbage collection proposal, and this will allow like better integration with the JavaScript garbage collector, and in turn you can do stuff like with frameworks and just various things like DOM manipulation. So the next thing is being able to call web browser APIs directly. So rather than having to go through JavaScript, you can just go and call like a web API directly without having to go through JavaScript. So there's this thing called the Web Interface Description Language, and this is basically defines how browsers, the types, the return types, and the parameter types that that browser APIs take. So we need to have kind of bindings to those APIs. But the problem is that the browser types are quite complex, right? So I was saying that WebAssembly only takes numbers. So we need to do something clever to be able to essentially allow WebAssembly to call those APIs directly. And this comes down to this binding to the web IDL types. And this is going to happen through this thing called interface types, which is basically like definitions of how you map complex types back to WebAssembly. And by solving this problem, by solving the problem of the browser being able to, WebAssembly being able to talk to the browser directly, you actually solve like a whole host of other problems, because you solve the problem of WebAssembly being able to talk to another language that has different types. So if you can create this like intermediate representation, then you can interact with like a whole bunch of different things. So not only the browser, but potentially other languages and other WASM like programs that were compiled from different languages. So it allows for this kind of the interface types allows for this like universal kind of communication. So concluding, so will this change the web forever? The short answer to me is yes. I think it already is, and it already kind of has to some extent. But to the full extent in the future it's kind of an unknown. It's still kind of a bit of a wait and see kind of thing. At the moment, I think like WebAssembly really augments the current web platform. It allows us to do things that we couldn't do necessarily before. So for example, like AutoCAD compiling their native desktop application, which is like a 35-year-old code base to the web, is super cool. Yeah, so I mean, for me right now, there's these three solid reasons that WebAssembly is powerful and will change the web, is because you can have consistent performant code, you can compile from libraries in different ecosystems, so you can, for example, the barcode library, the C barcode library that eBay used, you can just pick and choose libraries from different ecosystems and say, yeah, I want to use those. And the last one is that it kind of solves this issue that we've been having around with native code and plugins. So it allows us to, it's easier now to envisage a web without the need for plugins. So yeah, I guess the last thing I kind of want to talk about is with JavaScript, that I think it's hard to deny that JavaScript has pretty much changed the world, or at least the tech world. So JavaScript, started off as this little browser language, and now you've got things like it's running in the backend with Node, or it's running on IoT platforms with things like Johnny 5, or it's making cross-platform applications with things like React Native, or desktop applications with Electron. So it's just gone on and spiraled to become so much bigger than just like a web scripting language. It's kind of become this ubiquitous language that just kind of runs everywhere on every device. And I think that we're still in the early stages of WebAssembly. We're still kind of at this MVP stage. And it'll be really interesting to see where WebAssembly goes in the future, and if it goes down this path of like becoming this super ubiquitous platform. So to give you like, to put that into perspective, there's a guy called Solomon Hykes, and he was a co-founder of Docker, and he said, if WASM and WASI, so WASI is the WebAssembly systems interface, it's a way to interface with things like files and the network and all that kind of stuff. So he said, if WASM and WASI existed in 2008, we wouldn't have needed to create Docker, because it's just kind of like this universal format that languages can compile to, and so many different languages can interact with. You just write it once, and it just runs on the WASM runtime. Yeah, so I think it's just a really interesting point in time to kind of be looking at and thinking about WebAssembly. That's me. Thank you very much.